All right, guys, in this video, we're going to talk about the rest of 2.3, and this is just going to round out our little section here on the polynomial functions and modeling. So we have a big theorem here. It does have a fancy pants name. It's the intermediate value theorem. It's actually a pretty large concept that gets taken all the way up through fairly advanced math classes. And it's not something that's difficult to understand, but it's a big idea that gets used a lot. So in the intermediate value theorem, it just says if A and B are real numbers where A is less than B, and f is continuous on A to B. So this is giving you the x values from A to B. Continuous meaning that there's no holes or breaks or asymptotes in the graph, okay? So if that's the case, then f takes on every value between f of A and f of B, meaning that your y's will have a value everywhere within that interval, which seems like a common sense, but it's one of those ideas that actually gets used in very advanced math topics down the line. So now you can say, I understand a math topic from really advanced math classes. It just says that if you have a continuous function that has no breaks, and then on everywhere in that interval of your x values, you're also going to have a y value because there are no breaks. Okay. Now the next one, this is another theorem. It doesn't have a fancy pants name, but it is pertaining to polynomials of odd degree. And this one is another one that is kind of like common sense once you think about it. But it just says every polynomial function of odd degree has at least one real zero. And you think about it, like we've talked about the fact that you don't, like I could have something like that's to a third power, right? I could have something like x to the third power, and you know, it could be like plus x squared or something. I'm not sure what this would look like without graphing it or without doing more work, but you could have something to the third power that ends up having 3 zeros. We talked about this in yesterday's video. In the last video, we said that whatever the degree is, the highest degree, that's how many potential zeros it has. However, there are some situations where maybe that curve could have happened above the graph. Or if you're looking at like the parent function for x cubed, it doesn't really like dip back down so much. Okay, so in some situations, there would only be 1 degree, but here's the thing. It says every polynomial function of odd degree has at least one real zero. There's no way that this thing could go down for forever and up for forever and be continuous without actually hitting the x-axis somewhere. Now, even functions can get away with it. So this is not pertaining to even functions. Say that I had something to the 4th power, but it had its little wobbles above the x-axis. There's no zeros in that situation, even though it could be to the 4th power. So I just want you to keep in mind, if it is an odd degree, it will have at least 1 zero. Even degrees can get away without having any. So anyways, there's that. So let's see, we got another example we're going to look at together here, actually a couple more in a row. In this one, it says just to find all the real zeros of my function, and they give me a pretty ugly function. So in this situation, this is one where I would resort to using a graphing calculator. I look at it and immediately that's what I want to do without even attempting to do that by hand because that looks kind of ugly. So that's what I'm going to do on this one. If it is particularly nasty, like decimals in it, I wouldn't even think about trying to put that, do it all by hand. Okay. So in order to solve this in a calculator, we just need to type it into my graphing. So let's see, I've got plus 0.1. We have x to the 3rd power. And then we have minus 6.5 x squared plus 7.9 x minus 2.4. All right, oops, too far. I want to go to the graph. Okay, now this guy, I don't feel like I see everything very well. Hold on, let me. I think I may have mistyped something. Let me go back. Okay. Oh, that's why. I swear. Okay. I have to erase all this and go back. So you have to be careful with the exponents. I just did that silly mistake where if you have like a special exponent, you got to make sure you tab over and then but I looked at it and I was like, that does not look the way it should. And that's something I want you guys to get used to. Don't just take the calculator's word for things. If it doesn't look the way you know it should, go back. Okay, that looks better. Okay, it looks something like this. Now, in order to figure out my zeros, I'm going to say calculate, find zeros. And it will tell me exactly where all the zeros are. Okay. Some of them that are particularly hard to see are over here on the right side because it seems like there's not going to be that, like all those separate ones, it seems like it might be less than what the maximum possible could be. But I think we actually have 4 here. So I'm going to list them all out. Okay. This first one we see is negative 3.0997. If we round that to the nearest 3 decimal places, it actually ends up making me go to negative 3. I guess 1, doesn't it? All right. So that would be my x. Y was 0 because it's one of those zeros. All right. I'm going to tab over. And this one gives me an x value of 0.5. So we have 0.50. I can tab over again. I know this is not 100% into the screen, but you just see I'm tabbing over. I'm going to go 1.1330. And then the next one, 1.367. Just like that. So I get my zeros. Yeah. All right. The next question. If we have a packing company, we've seen a problem similar to this in the past, but here we have a packing company. They're taking a piece of cardboard, they're cutting the corners out, and they're trying to fold it into an open box. All right, so they're telling me that they need the volume to be 484 inches cubed, which is a little different than the question that we had last time we worked a problem similar to this. Because last time they didn't tell me what the volume needed to be. They'd ask me how can we maximize the volume, which is a little bit of a different question. All right, so squares are going to be cut from the corners here. My original size cardboard is 20 by 25 inches. And then it says that we're going to fold up those sides to create an open box. Okay. What size squares should be cut? All right, so we're going to look here at this guy. All right. Now, I'm not going to draw all over my picture because I don't want to mess it up, so I can't use it in class. But I know that all the way across here is 25. But if I look at the distance between where the squares are going to be, remember how the square is going to be of length x. And we have 2 of those on this side, x and x. So between those two, that's actually going to be 25 minus 2x. And we get a similar situation going on with the other ones. So let me find something I can write on. Okay. So over here, if we know all the way across is 20, but then we cut out these little x's, this is x plus x, we would be taking 20 minus 2x. Okay? Now, when you fold this, when we cut out those little things and we fold it, you think about what's happening. This little piece right in here folds to be up, and that's a distance of x. That gives me the height of that box when it is folded. So in order to talk about the volume of this box, okay, remember how volume of a rectangular prism is length times width times height. Well, the height of this guy is going to end up being just x, because that's the height of those little flaps when they get turned and folded up, okay? But then we've got here our length and our width. Those are the values that we'll have once this thing is actually folded into a box shape. So for my volume, we're going to take that height, the length times width times the height. It doesn't matter the order that you write it, but I typically put, if I have a lone variable, I tend to write it first. Length times width times height, just multiply them all together, all three of those values. Okay. Now, they're asking in this one, what size should the squares be cut? So what does x need to be in order for my volume to be 484? Okay? And so that's what we're going to do in here. We're not trying to maximize the volume this time. We're actually just trying to figure out what does x need to be in order to make that the volume. And you can solve this a multitude of ways, but there is a way in your calculator, which I don't know that we've talked about in all my videos. So I'm going to bring up a different way to do stuff. What I'm going to do is I'm going to break this into two equations. In one equation, I'm going to put the left side. Okay, so I've got f of x equals 484, and that's it. Then we're going to put in another line, and we're going to write out what I have on the right side. Okay, just exactly how I have it. You don't have to do more work than that. Oops, I got too many negatives in there. Minus 2x. Close. All right, I'm going to double check, make sure I've got it typed good. Okay, so one of my equations was the left side. The other equation is my right side. Okay, and what we can do is just go graph it, and we can see where these two things cross. Where these two things cross are my possible answers for x. So, and if you have trouble seeing it, you can usually go to calculate and then go through, where did it go? Intersection. I skipped it. And it will make sure that you see exactly where it is, because sometimes when you just kind of tab around, sometimes you don't actually end up getting exactly it. So the x values I'm getting here are x equals 1.222. Okay. Another I'm getting is x equals 6.871. And then my last one over here, I'm just looking at this little value in here. This is 14.406. Okay? Those are the different ones I'm getting for x. Now, here's the deal. Not all of those are necessarily valid answers. So what I want you to think about is the fact that this is a geometry problem. And there is a value in here that if I actually used it in the problem, it wouldn't make any sense. Think about this 14.406. If I looked at having a side length where I had 20 minus 2.14.406, this would end up giving me a negative width. Doesn't matter what the number is, because that's a negative width, it's going to end up being something that's not a valid answer. And you can check that with the others as well. 6.871, that's okay to have. 20 minus that, that's okay. 25 minus 2 times that number, that's okay. Same thing with this guy. If one of these had been negative, you would know that that wouldn't work, because there is a height of just plain old x, and that would be bad. So we actually have two options that we could tell them they could make for these squares. One option is we could have these squares be 1.222 inches by 1.222 inches, or it could be 6.871 inches by 6.871 inches. You get two different possible sizes for those x values, okay? All right. Last little thing, guys. We haven't really talked about regression. I know you guys did plenty of regression back in Algebra 2, but just to make sure that we are on the same page and everybody has seen at least one in class before I expect you to be able to do them. we're going to talk about a regression problem, okay? Now, you also should have learned that there's an easy way to determine if something is a linear function or if it is not, okay? If they have successive differences that are common, then you're able to see what kind of degree it is by looking at which level of differences were the same. If you look at also your x's, your inputs have to be equally spaced. So you're seeing in this problem, these are spaced by 2. So they're equally spaced. My y's, if the first difference is the same, then it's linear. Okay. But if the second difference is the same, it's actually quadratic. If the third difference is the same, it's cubic. And I can keep going up that list. Okay. So what I can do is if I know that relationship, then I can use that to tell me if it's going to be linear, quadratic, cubic, so that I can tell the calculator which regression model to follow. Okay. It's also possible that they could ask you which type of function it is without using a calculator, even if they didn't ask you to give the actual equation. So keep in mind that this is an important skill for us to figure out, and then we'll be able to do the regression model in the calculator. So the first thing we're going to do is find the first difference. Okay. So I'm going to look between 3.1 and 2.9. If I do 3.1 minus 2.9, this is 0.2. If I look at 12.9 minus 3.1, this is 9.8. Okay. If I look at 41.9 minus 12.9, this is 29. And some of y'all might be like, well, it's not the same, so I can just stop and I know it's not linear. You're right that it's not linear because these are not the same. But that doesn't mean I can stop because I have to keep going until I find which difference is the same. If I do 99.7 minus 41.9, that gives us 57.8. Then over here, 195.9 minus 99.7, this is 96.2. So obviously it's not linear because the first difference was not the same. So then let's look at the second difference. That means I'm going to find the difference of the differences. And I know that sounds crazy, but that's what we do. So 9.8 minus 0.2 gives us 9.6. Then if we do 29 minus 9.8, we get 19.2. Okay, that's not turning out to be the same either, but we got to get we got to continue getting this whole row. 57.8 minus 29 is 28.8. And then 96.2 minus 57.8 is going to give you 38.4. So we can see that the second difference is not the same. But then we can look at the third difference. Yeah? Third difference. Okay. 19.2 minus 9.6 is 9.6. 28.8 minus 19.2 is 9.6. Hey, look at that. 38.4 minus 28.8. This is 9.6. You do need to make sure that you go all the way across. It's possible to get two of them that are the same without all of them being the same. So here I do see the whole row for the third difference is the same. So that's great. That tells me that it is cubic. So when I go into my calculator, I'll be able to tell it which regression model to use. All right, on these, I know a lot of you guys got used to the TI-84s, and that's awesome. We have those in class, so you're welcome to use it, but I'm going to show you how to do regression on this calculator. From the home screen, there is a regression. I don't know if y'all can see it on the calculator screen here, but it is right below the grapher. Okay, so one I have highlighted here in the middle on the bottom there. Looks like a scatter plot with a line through it is what the app looks like there, okay? And it opens up straight into a list for you to put your X's and your Y's. So take a moment and we're going to list all of those out. I'm gonna have to double check this because I don't trust myself to type things right the first time. So I'm gonna have to double check and make sure I have all my numbers before I feel good to keep going. Okay. All right. Okay. 47.9, 41.9. Okay. All right. Cool. So once you have all of those typed in, that's when I'm going to hit go up to the graph. And I'm going to select the regression over here. So go up and over, hit OK. And I have to select, we said it was going to be cubic. So we're going to go to the cubic model. It gives me this little mean point first. So don't write down what they have here. I typically just like move my cursor down and then it pops out with my equation down here. So I don't know if y'all can see that or not. I've done these on both this calculator and on the TI-84s, and on both of them, we have to be mindful of this B value because the B value is a little bit wacky. So, is it the B? I might be thinking of it. No, I think it's this one. Oh yeah, because they have this E. Okay, they're giving you scientific notation there. This number is so little that your TI-84s don't even register it as having a number. They just say your B is 0. And that's what I would expect you to have as well, because this is saying 1.905, blah, 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 e to the negative 15th. That is a teeny, 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 tiny number. So your little B value in front of the x squared, like I say on the 84s, it's going to show those as having a 0. So my function on this one, I'm just going to write it out. I know it was pretty blurry when I was trying to show it, but you'll end up seeing this x cubed. I'm not going to worry about it, the x squared term, okay, because it was so little. But then my plain linear term and my constant there. Ta-da! There's our equation. And that is to model those points. All right, y'all, that is it for this section. Good luck on the assignment, and I'll see y'all in the next one. Bye.